بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome back. Outcome number 12 as mentioned in the textbook, page 245 and 246. Solve problem 9.3. Before that, let us discuss these questions. First one, find the time constant for the LR circuit shown. The time constant is tau RL. It is L over R. Simply substitute from the graph. L it is 550 millihenry, so it is 10 to the minus 3. Then R it is 1.33 kilo. Kilo it is 10 to the 3 ohms. Then it's easy to find that. Tau is equal 4.14, almost 4.14 times 10 to the minus 4. And the unit is second because it is time. It is time constant. Now for the second question, a resistance with 3 ohms, this is R, an inductor L, an opened switch, and a battery of VMF, this is the VMF, are connected in series. Let us draw it. The resistance, the inductor, and a switch, and the battery. R, L, VMF. The current grows up to 225. This is current at some time within 26 milliseconds. This is the time. 26 times 10 to the minus 3 second. This is the time needed to reach this current, 2.25. After closing the switch, this circuit is a growing current circuit. To reach the steady state. Now, for growing current, we have this formula, I equals I maximum 1 minus E minus T over tau. What the question asks me to find is find the characteristic time constant. So I need to find tau for the RL circuit. Then the missing item is this tau. To find it, let us extract this equation. Divide by I maximum. I divided by I maximum becomes 1 minus E minus T over tau. Now make the adding by the inverse. I will take like this, E minus T over tau equals 1 minus I over I maximum. Now if you take the ln for the both sides, I will have ln E minus T over tau equals ln 1 minus I over I maximum. Ln E to the minus T, it is minus T over tau equals ln 1 minus I over I maximum. I need tau. So if you do the cross multiplication like this, we'll take that tau times ln 1 minus I over I maximum equals minus T. So tau becomes tau RL, of course, it is minus T over that length. Almost done. Now substitution. Minus T to 26 milliseconds. 26 milliseconds 10 to the minus 3. Len 1 minus I. The I is 2.25 divided by I maximum. I maximum, we reach it at steady state. For steady state, I equals I maximum, which is VEMF over R. The VEMF is 30 and R is 3. So the answer is 10. VMF it is 30 and R is 3. Now put it here. I maximum it is 10. Do the calculation. The answer will be 102 and the unit is second, or 102 millisecond. That's it. Now let's go to outcome number 15. Understand the equations related to the RL circuit, as mentioned before in the last question. An inductor and resistor are connected in series to a battery in circuit shown aside. Both S1 and S2 are open. Both switches are open. At t equals 0, we close S1. So here we have closing S1. What is the meaning of that? Growing the current. So closing S1, growing current. What is the meaning of a growing current? It means that I equals I maximum 1 minus E minus T over tau. What things that we have for this equation? First of all, we can find the I maximum. At steady state, I equals I maximum, steady state, which is VEMF over R, 36 over 0.1 times 10 to the 3. Here is the resistance, here is the voltage. So the maximum current is 0.36 ampere. What else? We can get tau. Tau for RL, it is L over R. From the circuit above, L is 25 millihenry. 25 milli, it is 10 to the minus 3, divided by R, which is 0.1 kilo ohm. 0.1 kilo ohm 10 to the 3. So what should be the answer? It is 2.5 times 10 to the minus 4 second. Do I need something else? I don't think so. Now substitute here. I equals I maximum, it is 0.36, 1 minus E minus the time needed is 0.203 millisecond 10 to the minus 3 divided by tau. Tau it is 2.5 times 10 to the minus 4. Do the calculations. It is 0.2 amperes. For part B, how much energy delivered by the battery? This question is the same as in the book. To find the energy delivered, you need to integrate the power. The energy, U or E, it is integration of the power for the time interval. And the power here, because we need the power for the battery, we must have or use this equation precisely. I times DEMF. This is the power, then dt. Substitute for the current. The current, while growing up, it is I maximum 1 minus E minus T over tau dt times V. Times V. Then dt. Now it becomes I maximum, DEMF, they are constant, and the integration is 1 minus E minus T over tau over dt from 0 to some time. Now let's substitute. I maximum is 0.36. The battery is 36 volt. Integration, the time from 0 to 0.203 millisecond. 1 minus E minus T, it is our variable, over the time constant, it is 2.5 times 10 to the minus 4, all dt. Put it in the calculator and find the answer. The answer will be about 8.29 times 10 to the minus 4 joule. Now we will go for new idea. After 10 minutes, so the 10 minutes is very long time. From closing S1, we open it and close S2 simultaneously. So we open S1, S1 was closed, we open it. At the same time, we close this one. Now we have LR circuit, and it is a decaying circuit. So now we have a decaying circuit. Now we have, because we have no power supply, a decaying circuit. What is the meaning of decaying circuit? That means I equals I naught E minus T over tau, without the one minus, without it. And I naught it is the same as I maximum before, which is 0.36 ampere. Now, after 10 minutes from closing S1, we opened it and closed S2 simultaneously. Find the current flow into the resistance after 0.203 millisecond of this procedure. So, to find the current at that time, I0 it is 0.36, e to the minus, t it is 0.203 times 10 to the minus 3 over the time constant, it is 2.5, I think it's 10 to the minus 4. Some students may be disturbed about this 10 minutes. It has nothing in the question. Don't look to it. It is only to tell me that I reach the steady state before I reach this opening and closing for S1 and S2. And if you do your calculation, it would be almost 0.16 ampere. Now, how much energy delivered to the resistor in the time interval 0 to 0.203 after opening S1 and closing S2 simultaneously? Here we have to find the energy delivered in the resistance. So don't use IV like for the battery. Use I squared R to find P. It's a very important thing. So for battery, use I delta V for battery. But for resistor, you must find I squared R for the power. So the energy E delivered by the resistor R, it is the integration of B dt, integration of B, it is I squared times R dt, and I is a decaying current, so it is only I0 E minus T over tau, but I need to square it because it is I squared times R dt. Put the numbers here from 0 to 0.203 millisecond. I0 it is 0.36, E minus T over 2.5 times 10 to the minus 4, and we want to square all of this, multiply by the resistor, which is 3 times dt. Use your calculator to find the answer. It would be 3.9 times 10 to the minus 5. Now for outcome number 14. Calculate the energy stored in a magnetic field. The question says, how much energy is stored in the magnetic field of the inductor at steady state of the circuit? As we mentioned before, the steady state means I equals I maximum, which is the voltage by the battery over the resistors in the circuit. It is 36 and the resistor is 0.1 kilo ohm to the 3, so it is 0.36. Now it's easy. The power, the energy in the magnetic field, it is 1/2 Li squared. 1/2 L is 25 millihenry 10 to the minus 3, and the current is 0.36, and we square it to find that the energy is 1.62 times 10 to the minus 3 joule. Now for outcome number 15. Sketch graphs for an LC oscillator showing the variation of charge, current, electric energy, and magnetic energy as functions of time, and the period of the oscillation t. I have two questions now. First one, we will start with the electric field. The second one, we will start with the magnetic field. Let's go. Consider the circuit shown in the figure. The switch has been at A for a very long time. So the switch was here for a very long time. That means the capacitor is charged, and it is fully charged. By fully charged, we can find the Q maximum as the definition of the capacitance, C times VEMF. Now we can substitute. C, it is 60 microfarad times V, it is 9 volt. By multiplying, we have 540 microcoulomb. This is the Q max. We find it. If we move the switch to B, now there is a changing in the capacitor. We move the switch to B like this. What happens? The electric energy will be converted completely to magnetic energy. As we know from the oscillator, LC oscillator, that the electric energy changed into magnetic energy within 1/4 period. So UE becomes UB after T over 4. So T over 4 equals that time. How much is it? It is 228 milliseconds. 228 milliseconds. So T equals almost 912 milliseconds. This is the period. By period, we can find omega. Omega, it is 2 pi over T. So it is 2 pi over 912 millisecond 10 to the minus 3. That is almost 689 radian per second. Assume there is no energy dissipation and answer the following. Find the maximum charge. We find the maximum current. As you know, Q is a function of time, and since initially Q is maximum, so we can express it by cosine function. So Q maximum cosine omega t. And if you want to find I, it is dq by dt. If you derive the charge, Q max constant, the derivative of cosine, it is minus sine omega t, and the derivative of this angle is omega. Now I equals I maximum sine omega t with a minus sign. That means I maximum, if you compare the equations, it would be Q maximum times omega. Now Q maximum, it is 540 microfarad 10 to the minus 6, multiplied by omega 689, the answer would be 0.372 amperes. C. Draw graphs to show the changings of QI, UE and UB for 2 full cycles. I need to draw 2 full cycles. We will start with the charge function. So Q, it is a cosine function. So we need to draw a cosine function from maximum to 0, then minus maximum, again go to 0, maximum, 0. It is alternating, maximum 0, then maximum. I think these are 2 full waves. Now, where is the period? The period for full cycle is here. This is a full cycle. And how much is the period? It is 9.12 millisecond. This is the time axis. And the Q maximum is 540 microcoulomb. This is the function of the charge. What about the function of the current I? I is measured by amperes. We note here it is a minus sign function. So starting from 0 because it is sign 0, 0, and go to the minus. This is the current. It is a sine wave or a minus sign exactly. Now this is the period, 9.12 in milliseconds, and the maximum current here, it is 0.372. Here minus 0.372. Now, if you want to draw the energy it is UE, it is 1/2 Q squared over C. So you need to square Q and divide by 2C. Then UE always greater than 0. It is positive. Square the Q, make it positive every time. And 2C, they are positive integers or numbers. So UE always positive. Now, this is the maximum energy. It will drop to 0 after 1/4 cycle. Then it will go again maximum after 1/2 cycle. Then drop again to 0 after 3/4. Then after full circle cycle, it is again maximum. For the second cycle, draw this. This is U of E in joules, and we can find U maximum by Q squared maximum over 2C. If you substitute C and Q maximum from here, C 60 microfarad and the Q maximum is 540 microcoulomb, we can find the maximum energy as 2.43 times 10 to the minus 3 joule. So the maximum is 2.43 multiplied by 10 to the minus 3, put it here as a factor, times 10 to the minus 3 joules. And don't forget that this maximum energy in the electric field becomes maximum but after 1/4 of the cycle as a maximum for the magnetic energy. So if you want to draw the magnetic energy, you will start from 0 as its current starts from 0. It will start from 0 to a maximum, then 0 again, maximum, and so on for the first cycle, then for the second cycle, and so on. So here is one cycle. This is 912 milliseconds. This is the time milliseconds. And to complete the second cycle, go here. And the maximum is 2.43, and UB would be in millijoules, 10 to the minus 3. Now, to master our learning, let's go to this question. Consider the circuit shown in the figure. Switch S1 has been closed for a very long time. This S1 is closed for a very long time. That means we reach the steady state for the inductor resistance circuit. For such a circuit, we can find I maximum. I maximum at steady state, it is VEMF over R. VMF, it is 3.6 and R is 5. Divide these, 0.72 amperes. So this is the maximum current. We find it, the maximum current, 0.72 amperes as shown here. Let's go back to the question. Switch S1 has been closed for a very long time. If you close S2 and open S1 exactly at the same time, the current will decay to 0. Decaying the current to 0 needs 1/4 cycle, the same as the last question. So this time 22.5 milliseconds, it is 1/4 cycle. So T over 4 equals 22.5 milliseconds. That means T is 90 milliseconds. That happens if we open S1 and close S2 at the same time. Now we need to find the maximum charge. To find the maximum charge, you need omega. Omega, it is 2 pi over T. 2 pi. And T, it is 90 microsecond, 10 to the minus 3. So the answer would be 69.8 radians per second. Now we can find Q maximum. As Q maximum, as we mentioned in the last question, times omega, it is I maximum. Then Q maximum equals I maximum over omega. We have I maximum from A, it is 0.372 over omega, it is 69.8, and the answer is 0.0103. Almost, it is rounded column. Now for C, draw a graph to show the changing of QI, UE and UB. Here we need to take care of something, but first let's draw the current I in amperes. The maximum value is 0.72. The period 1, 2, 3, 4. Here the period T is 90 milliseconds, and this is the time axis. Now for this circuit, it starts with current, not with charge. So the current would be cosine. So the current is cosine from maximum to 0, then negative maximum, then it will go up to 0 again and comes here. This is one cycle. The other cycle is like this. This is I equals I maximum cosine omega t. To find the Q, what should you do? We know that I equals dq by dt. So Q should be equal to the integration of I dt. Integration of I maximum cosine omega t dt. What is the integration of the cosine? Yes, it is sine. And omega, so it is sine over omega. So the answer is I maximum over omega sine omega t. So here the function is positive. Then the charge will be a positive sign, not negative like previous question. So here Q in coulombs, the maximum value is 0.03, 0103. .0103. The period 1, 2, 3, 4. Here the period 90 milliseconds. This is the time. And we need to draw a sine function, a positive sine function. So go up, down, then negative maximum, 0, maximum, negative, and that's it. Now for the energies, UB equals 1/2 Li squared. If you need UB maximum, you need to take I maximum. 1/2 L from the circuit, it is 220 millihenry. 220 millihenry 10 to the minus 3. And the maximum current is 0.72, and we need to square it. And the answer almost 0.57 joule or 57 millijoule. Again, this will be equal to also the energy, electric energy maximum, but after 1/4 cycle. Now for the magnetic energy in this circuit, it is maximum at the beginning. because the current is maximum. So here is UE, and this is a maximum value of 57 U in millijoules and T in milliseconds. 1, 2, 3, 4. This is the period. The period is 90. Now draw a maximum at the beginning, drop to 0 after 1/4 of the cycle, then rise again, down again. This is a full cycle, 2 times in each cycle for the energy, but for the charge and the capacitor, it is only 1 time in 1 cycle. Now let's continue. This is the energy, and for the electric energy, also in millijoules, time in milliseconds. 1, 2, 3, 4. This is the period 90. But for the electric energy now, it starts from 0 because the charge is 0 at the beginning, as you see here. So from 0 up to a maximum, the same maximum of the magnetic energy, and so on. That's it, and here 57. So when the question asks you to draw I from Q or Q from I, don't memorize the thing. You should do differentiation if you have a Q to know what is the function of the current, minus sign or plus sign. And if you start from current and you need charge, you need to make integration. Again, you need to take care of the signs. Now, the outcome number 16. Describing the alternating sinusoidal current induced in a circuit containing a sinusoidal time varying source. Draw the current time graph and the voltage time graph for the ohmic resistance shown. First, we need to remember that the ohmic resistance opposes the current flow by collisions. It has no induction. It cannot charge or discharge like capacitor. So the current would be 0 if the voltage is 0. The current would be maximum if the voltage is maximum. They are in phase. We name that they are in phase. So I and VR are in phase. The phase difference between them, phi is 0. This is phi phase difference, not the flux. Phase difference. And we must write I in small letter. Small letter I and small letter V, they are instantaneous values. Now, we know that VR for the alternating current is V, this is the maximum V, sine omega t. And I, instantaneous current, it is the maximum current, sine omega t. Why this is so? Because I equals V over R. V is V sine omega t over R. We name V over R as the amplitude of the current, sine omega t. So we name this I, capital I, and VI maximum values. Sometimes we name them as amplitudes. They are the amplitudes for the sine functions. But small I and small v they are instantaneous values. Now to draw it, I need to draw a sine function for both of them. You can draw as you wish. This is maybe I, and this one is the voltage. They are grow with each other and decay with each other. This line represents the instantaneous value at any time. Here is the current, instantaneous current, and that one instantaneous voltage. The amplitude, this amplitude is maximum current, and the blue one is the maximum voltage. Don't say that the current is greater than the voltage. It is not in scale. You cannot compare the magnitude of the current with the magnitude of the voltage. They are two different quantities. So don't think that the current is greater than VR. We can draw the same situation like this. This is the voltage, and this is the current. It is a scale, just a scale. So this is the instantaneous current, and that one instantaneous voltage, and these are the maximum values, V and I. Here we have one period, and this is the time. This axis represents two quantities, V and I. So it is a double axis. Each axis has its own scale, VR and I. Okay. Let's go to the second question. Or this is the drawing by the book. It's lovely drawing. Now we want to show the phasor diagram. Consider the circuit shown, then pick the suitable phasor diagram from the following photograph that fit for this circuit. First, what is the phasor diagram? What is the phasor? The phasor is a rotating vector. It should be counter clockwise. If you draw it clockwise, it is wrong. Counterclockwise, and it begins at the origin, or it locates, or its tail at the origin. So you can draw the phasor like this. It's okay, but indicate the direction. It is like this. It is clockwise. If you draw it like this is wrong. You cannot claim clockwise direction. Okay? So it should be counterclockwise and starts from the origin. It could be in the third quarter, no problem, but it should be measured from the positive x-axis counterclockwise. Or you can simply put like this. You can put like this and write omega, no problem. Now, for R and alternating current source, we mention here they are in phase. So the phasor of the voltage should be on the same direction of the current phasor. Which one is correct? Here, V and I, they are separated. No, this is wrong. I, V, also wrong. V, I, wrong. Here we have the two phasors in the same direction. So this is the right answer. But I need you to remember that the length of the phasor is the maximum value, and the projection of it on the y-axis, it is the instantaneous. It is the opposite of that diagram. Here the line, the graph itself, it is the instantaneous, and the projection is the maximum. Here it is inverse. The length is the maximum, and the projection on the y-axis, it is the instantaneous. Yeah? And it is clear why we say that. This is the opposite to the angle. What is sine omega t? Opposite, which is VR, over hypotenuse, which is V. Now multiply VR equals V sine omega t. Okay, so VR, it is the projection, and the length of the phasor is the maximum value. Thank you for watching. See you in the final video to the rest of the outcomes.